In this lecture, we're going to talk about phase changes and the kinetic energy that goes into and out of a substance in order to cause it to change phases. A phase change is actually a two-step process. First, what's going to occur is a substance's temperature is going to increase or decrease in order to reach the point, the temperature point at which it's going to melt, freeze, boil, vaporize, whatever phase you're going to look at, whatever phase change. And then the second part is that the intermolecular forces need to be overcome in order to have the entire substance change phase. Let's look at an example of this before we go through the notes. In this animation, we're going to look at a block of ice, and we're going to look at how adding heat will cause the temperature of the ice to change. But what we're going to watch is we want to keep a close eye on this graph because it is not going to be a linear change as expected. So we're going to see the thermometer rise. This thermometer is the heat that is being applied to the system from this Bunsen burner once it turns on. This graph where the temperature is not reflecting this thermometer. So it's a little confusing. Imagine there's a second thermometer that is in the water in this ice cube. And this graph will be reflecting the temperature of the substance. So as we turn on our Bunsen burner and we apply heat, we see the graph starts to go up because the temperature of that ice is going to be getting higher. And we see the molecules, as we increase a little more heat, the molecules are going to be moving a little bit faster. But notice that the graph is starting to just sort of make a curve. It's not making a straight line anymore. And as we further increase heat, we see that the temperature of the thermometer, meaning reflecting the temperature that's being applied, is going up. But the temperature of the liquid in there is not. So what's going on is that although we still have that substance getting warmer, the substance is gaining kinetic energy, but it is in the process of breaking the intermolecular forces. So as we can see in the substance right now, some of them are in the liquid phase, but some are still stuck in the gas phase. So this substance is not going to increase in temperature until every one of these molecules is now going to be able to be freed into the liquid phase. So I'm going to increase the temperature more. And we increase. And we see that we're still in a plateau where the temperature of the substance has not changed. Now that we have finally gotten all of the molecules to break their intermolecular forces, and now they are all free in the liquid phase, now as we add heat, we see that the heat of the substance starts to increase. So we can further add heat with our Bunsen burner to this sample. And again, we'll see that the temperature of the sample goes up. It's getting even warmer as we apply more heat. And now we start to see that some of these liquid molecules are moving up into the gas phase. And notice what's happening with our line. It looks like it's going to be going into a plateau. So as we've reached the maximum heat that can be applied to this sample, which is basically the boiling point of the liquid, we see that the temperature is not going to go up again. And the reason this is because we're waiting for all of these molecules that are in the liquid phase. They need to all evaporate or boil off into the gas phase before the heat or the temperature of the substance can increase. So we see the volume of the liquid has decreased because more molecules have entered the gas phase. And finally, all of the molecules have entered into the gas phase. So what we get is a stair-step looking curve where we might expect that changing the temperature when you're doing a phase change, we might expect that to be a linear relationship. We see that in fact that it's a stair-step, and this is an indication of those two parts of a phase change. So let's look at this in more detail. We've seen this animation before where heat is being applied to an ice cube and we can see a microscopic view of those water molecules. So I want you to watch as the kinetic energy of the molecules increases. We see that gradually the intermolecular forces, the hydrogen bonds, are broken. It doesn't happen all at once. It takes a little bit of time. I've paused the animation so we can see that the water is now a liquid. So we're going to reverse the process and we're going to remove energy in order to the molecules to go back together and for that liquid to reform to a solid. But again, I want you to watch for the two different parts of the phase change. We're going to see the molecules slow down. So first we have the temperature change. And then we're going to see the intermolecular forces start to re-adhere, which is the second part of the phase change. So now we can see heat is leaving the system, and we can see those intermolecular forces have started to reform. So when we look at a substance that is changing phase, and we first look at the substance's temperature change, we want to remember that the definition of temperature is the average kinetic energy of the particles. So when the kinetic energy is going up, the temperature is going up. However, when we get to the point where the substance is working on changing its intermolecular forces, whether that is they are breaking because the molecules move faster and farther apart when heat is added, or the reverse, meaning the IM forces are getting stronger because the substance is slowing down if it is losing heat to the surroundings. The substance's overall temperature cannot change until all of the molecules have either broken or reformed their intermolecular forces, because this temperature is an average kinetic energy. It's a measurement of the average. So with just when one or two molecules breaks free into the new phase, that's not going to be enough for the temperature to change. Here's a graph that is very similar to that heating and cooling curve that we saw when we boiled that substance in the animation. You need to be very familiar with this and be able to interpret this before we can move on to actual quantitative calculations of how much energy is absorbed or released. So what this is showing you is that as temperature increases, the substance is going to go from a solid to liquid to gas. So what's important to know is that at the horizontal, or we should say the diagonal, at each diagonal line, for example, from A to B, from C to D, and from E to F, that is where we have temperature being changed. At each of the plateaus, for example, from B to C and D to E, we still have energy being applied to the system. Energy is still increasing. However, we see that the temperature has not changed. So the indication that the temperature is going up from point A to point B, what that means is that at point A, you have a solid that is very cold, and it gets warmer and warmer and warmer until it reaches point B, which is presumably its melting point, or temperature at which it melts. At this point, it is still a solid, but it has an overall kinetic energy, or its average temperature has reached that of the melting point. From point B to point C now, we have that substance is not changing temperature. It is still at its melting point temperature. However, this is where all of those intermolecular forces are being broken down so that each individual molecule in this solid, we can see these individual particles, so that they can now separate from each other. So we have a complete solid at point B. At point C, the substance is half solid and half liquid, so it's like an ice cube in a pool of water. And by point C, we completely have a liquid. Now that every molecule is free to move in the liquid phase, now that liquid can increase its temperature up to point D. Point D would be the boiling point or vaporization point of that liquid. At point D, we have 100% liquid. At point E, the temperature overall is the same because the average kinetic energy of the sample has not changed, because we still have half of the sample is still a liquid and the other half is a gas. By the time we reach point E, now all of the intermolecular forces have been broken down, so every molecule or every particle in the sample is free to move as a gas, and now the substance can continue to increase in temperature. So it is important to note that from point A to point B, point C to point D, and point E to point F, when we are increasing the temperature, we are increasing kinetic energy. From point B to point C and D to E, when we are undergoing a phase change, kinetic energy effectively remains constant because what we can see is that the temperature remains constant. The case is also true here if we are removing energy during condensation or during freezing. We see that the kinetic energy remains constant. So we should consider what causes some substances to melt at a lower temperature than others. It has to do with something called specific heat and the molar heat of vaporization and molar heat of fusion. What we see in this picture is that there are two different blocks of a substance. One block, well, I won't tell you what they are, but what we want to watch for is we want to watch for how does ice, when you put ice on each of these blocks, and there's a ring here just to prevent the ice from melting and falling off the edge of the table, what you're going to see that ice melts faster on one block than the other. To tell you ahead of time, the blocks are not made of the same material, but they are at the exact same temperature. So first we put ice on one block. Not much is going on, as you can see. But let's watch what happens when we put ice on a second block. Instantly, the second block of ice we can see starts to melt. And as I had said, these are at the same temperature. So specific heat is the amount of heat a substance can absorb. It's also sort of the amount of heat or energy that a substance needs in order to raise the temperature of that substance by 1 gram by 1 degree Celsius. So let's look at a few different samples of materials and look at how their specific heat is how it affects the temperature that they will absorb. So the amount of heat that they will absorb based on their material. So first we're going to look at, we have a 5-gram cube of copper, and we're going to put it under the same amount of fire. We're going to turn on the Bunsen burner, and we're going to look at what its temperature is. So currently it's at 20 degrees C. Let's heat this copper. We're adding 150 joules of energy, and we see that it's gone up to 97 degrees. So let's try and keep that number in mind, about 98 degrees. Let's repeat the experiment with a block of silver. We're looking at the same amount of heat, the same mass of material. And we can see that its temperature went up a very, very large amount. So that same energy that we're applying is going to change the temperature of this silver much, much, much more. So in both of those animations, the different materials were able to absorb different amounts of energy because the different substances had different specific heat capacities. So again, specific heat capacity is a value, or it is a characteristic of whatever the substance is, and it's basically the amount of joules or energy that a substance is able to absorb before it changes its temperature. What causes one substance to absorb a lot of energy as opposed to another substance definitely has a lot to do with the intermolecular forces that hold that substance together. A second factor that determines at what point or how much energy is required to change the phase of a substance is the molar heat of fusion for that substance. And this is not how much energy it takes to change the temperature of the substance, but how much energy it takes to break down or to reform the intermolecular forces. And again, it depends on the strength of those intermolecular forces. So for example, a substance that has hydrogen bonding is going to have a very high heat of fusion. It's going to take a lot of energy to break down the hydrogen bonds. A substance that has London dispersion forces is going to require a very low amount of energy. In our next lecture, we're going to learn how to calculate the amount of energy for a substance depending on its molar heat of fusion and its specific heat capacity.